in to keep the ball rolling here because I'm sure everybody's we're getting long on people's Saturdays. But let me just go ahead and get started. So most engineers want to invent something. Invention is very admirable. To be the first person or group of people to create something that's new, desirable, and groundbreaking is very exciting. Unfortunately, in the early stages, the invention may not be safe or sellable. So that as the inventor, you may claim to be the first, but you may not be the first one to make money with the invention. Hold on a second. I gotta move some things around to be able to see the screen. All right, here we go. This is where companies come into play. Companies can take an invention and evolve the product to make it profitable. Evolution is about taking that invention and continually adapting a product line and evolving the product with reasonable new customer features to maximize profits. For example, Boeing has gone through hundreds of aircraft variants in the last 70 years, with Boeing delivering over thousands of planes, the main premise of a fuselage, 2 main wings, 2 engines, 4 engines, a tail fin, and 2 rear stabilizers has been very profitable for Boeing. They do not make drastic changes in the design, but little profitable tweaks with each new product. As it is very expensive to do large modifications to a product line. The same can be said for other industries like automotive. Henry Ford invented the Model T in 1908. It was one of the first mass-produced cars in the United States. Since that time, Ford has continued to evolve its vehicles, take small increments year over year to not disrupt the manufacturing supply chain, which can be very expensive, while working tirelessly to maximize profits. So how do these companies continue to push on this evolution more and more each day? And the answer is multidisciplinary analysis and optimization. It is a methodology that enables the analysis of an optimization of a complete system by explicitly considering important interactions and synergies between the disciplines. This results in designs that are superior to those found in conventional methods. So let's hear from the experts. Earlier this year, Phoenix Integration hosted an MDO panel of experts and asked them, why do you use MDO in your organizations? The first response was from Dr. Raymond Coloni of the U.S. Air Force Research Laboratory. Without reading the entire quote, Dr. Coloni stated, MDO is a design philosophy that strives to capture the physics that are driving the design and exploit these interactions to create unique capabilities and eliminate late costly defects. We next heard from Kentaro Sugiyama of Northrop Grumman Aeronautics Systems. Paraphrasing his comments, MDO consists of 3 components: the integration and automation of tools, the interconnections of various engineering disciplines, and the exploration and optimization of design, done to maximize physical performance and cost objectives. Next, we heard from Juan Montoro of Lockheed Martin Aeronautics, aka Lockheed Martin Skunk Works, and he stated, a complex system requires a grand trade-off or a balanced compromise of needs of many interdependent systems. It requires a set of processes and tools which facilitates an intelligent selection of design variables in order to achieve a desired outcome. Jim Guglielmo of Boeing, also a firm believer in MDO, stated the following: MDO is the automation of standard vehicle design process. We optimize for both performance and affordability of cost. We use MDO to prevent problems or late defects. And in his words, quote, I also view MDO as a risk reduction activity on a program, unquote. And it's not just the big aerospace companies, it's also the suppliers. Dominic Lundy of Aerojet Rocketdyne stated, MDO allows us to reduce cost early on. It allows teams to work together from the beginning to explore a lot more iterations and designs than ever could before. Essentially, it culturally changes the way that your organization does design and engineering. So let's summarize these benefits. Holistic system, team system approach to engineering design, make important decisions early, reduce program cost and risk, utilize existing digital assets, and create new innovations to allow your organization to win more business. So as mentioned earlier, my name is Tony Davenport, and as you heard, I'm the North American Regional Manager of Phoenix Integration. Regarding this presentation, I'm going to provide you with an update on the latest capabilities associated with a product called ModelCenter that Phoenix Integration creates, and how it is advancing the state-of-the-art of performing digital product engineering. I'm joined on the call by my colleague, Dr. Scott Reagan, Phoenix Director of Technology and Business Development. So feel free to go deep on your questions as we progress through this presentation. There will be specific stopping points where I will ask or we'll work through answering any questions that come up. So thank you all again for joining us this Saturday. So what are we going to cover today? We're going to cover how to perform MDO within ModelCenter and how good MDO practices, what are good MDO practices or best practices with it. We're going to expand MDAO into the cloud and the advantages of both the builder and of the workflows and the analyst. And I think someone early in the call prior to Adam's presentation had made a comment about some of the new aircraft that are coming out. We're going to talk about how these things enable that capability. And finally, a topic that's very hot today, integrating systems engineering to MDAO, its benefits and how it's done. So how do you take these system solutions, integrate those with analytical tools so that you can do validation of the system way early into design and throughout the production. So before we move on to MDO demonstration, in the demonstration, you will see how easy ModelCenter allows existing digital assets to be automated and integrated together to create a workflow. Once that workflow is created, we will then explore the workflow through making changes to the inputs to see how outputs of the design or the design alternatives. We'll run sensitivity analysis to look at the correlation between inputs and outputs and determine which variables in this multidimensional, multidisciplinary-based system directly or indirectly affects our design objectives. This is also very useful in understanding what values do not affect outcomes so that we know where to stop focusing our efforts, just as important. After this, we will use ModelCenter's built-in post-processing graphics to be able to utilize the data created from our MDO runs to make effective design decisions. In the demonstration, we will then use ModelCenter's built-in optimization algorithms to optimize the design and intelligently improve the product's performance. And although not shown in today's demonstration, yet still a capability of ModelCenter, engineers may make use of the probabilistic analysis to fully reduce risk increase reliability after the optimization is completed. This is tied to sustainability and warranty. One more thing, one of the objectives of today's presentation is to give you a basic understanding of the most recent upgrades to ModelCenter's MDO algorithms. Through a partnership with a company called Noesis, Phoenix Integration has taken a generational leap in our MDO algorithms. These algorithms come included in ModelCenter Explorer module. So if anyone on the call today is a ModelCenter user and have Explorer, you're getting these at no extra charge. And these updates include adaptive DOE, aka design of experiments, which adapt to the response functions for more accurate, more useful response surfaces. We have machine learning response surface algorithms to create higher fidelity surfaces in the same computational time. Interpolating response surface algorithms, smart response algorithms, local optimization, global optimization, multi-objective optimization, and all can be managed. All of these can manage failed runs. And then finally, push button optimization algorithms and wizards that we jokingly call optimization for dummies. So at this point, I'm going to play a video. It's going to last maybe about 15 minutes. And it's created to demonstrate MDAO, and it's done by some of our lead application engineers, and it shows best practices of MDAO. And it's going to be completed on a wind turbine example, which has similar aerodynamics and things like that as you would see in aerospace. So hopefully, I'm very confident you guys will understand the message and how this pursues. At this point, I also asked, is there any questions so far? Let me just check here. I don't see any coming in on the Q&A, so I'm just going to go ahead and move forward and play the video.
In this MDAO demonstration, we're going to be using a wind farm workflow that is comprised of the following disciplines: aerodynamics, structural, cost, and energy conversion for a single wind turbine, as well as logistics for the entire wind farm. When it comes to the design of a single wind turbine, we focus primarily on its geometry, such as the blade rotational diameter and tower dimensions. Of course, there is also the aerodynamics involved in the design of an individual blade, such as the airfoil shape for the different blade sections. Before moving on to an entire wind farm, we focused on optimizing the design for a single wind turbine so that we would have a competitive one to use. At first, we started off with roughly half of a megawatt in turbine power, which we got up to 4.6 megawatts thanks to going through the MDAO process. This demonstration will cover how we went from a freshly created workflow to having optimized designs for a wind turbine and wind farm. Creating a multidisciplinary workflow such as this one in ModelCenter is easier than most would think. Let's look at how we can add an additional component here using the Excel plugin that we offer. In this case, this component is going to serve as a generator's catalog by using a predefined spreadsheet that we created. The plugin automatically detects cells that have been named and suggests them as variables to import. From the plugin menu, we can also launch the spreadsheet itself so we can visualize and verify that everything is correct. As you can see here, we have 3 cells that have been named generator type, generator cost factor, and generator efficiency. If we launch the advanced properties for one of these variables, we'll see that we have additional parameters that we can specify, as well as the range. So this feature allows you to pick one specific cell in case you hadn't named the cell before. As you can see, we have units as an option, and right now it's empty. So let's see what happens when you attempt to link this component and this variable to one that has units. As you can see here, the auto link feature popped up, so it recognized 2 variables with the same exact name. But we also got a warning sign saying that the units don't match. One is unitless while the other has dollars per megawatt. So here we can expand the details for the warning message. Let's go ahead and finalize connecting this component to additional analyses. Once again, using the auto link feature, and we can here verify that the connection was correctly made. Once we have done that, we can go ahead and fix the units mismatch issue by just entering units for that variable. Once that's done, the warning sign goes away automatically. So now that we have this component, the workflow, we can run the workflow. So that was a single execution of it, and see how the values from the generator's catalog propagate to other components, such as generator efficiency and generator cost factor. Those values are coming from the generator's catalog. So right now this field is editable entirely, which means you can enter any values for generator type. We know that could be an issue because the spreadsheet can only take 3 values for generator type. So we can go ahead and specify those predefined values so that if anyone else decides to use this workflow, they won't be able to enter incorrect values. As you can see here, it becomes a drop-down. So from there on, we can pick different generator types. The variables generator cost factor and generator efficiency will update automatically, and once we run the workflow, those values will propagate to the other components that are linked to them. During this demonstration, we'll take the following MDAO steps. First, we'll start with a screening DOE to get a lay of the land of the design space, to just get a generic understanding of it. Next, we'll go with the sensitivity analysis to understand which variables are the key players and have the greatest effects on our responses. Then we'll go down to narrowing down the design space by identifying trends that make good designs, and which will give us new design variable bounds. Once we have identified a feasible and interesting portion of the design space, we'll go with the targeted DOE over the desirable promising pocket to further explore the region. We'll then use the data generated from the target DOE to identify a good starting point so that we can feed that into an optimization. And then lastly, we'll go with 2 optimizations, one over the wind turbine design and then one for the wind farm. So let's start with the screening DOE. Back to the finalized workflow in ModelCenter, we can go ahead and launch the adaptive DOE tool. Once we have it ready to go, we can start adding design variables to the design of experiment setup by simply dragging and dropping them from the component tree. Once we have one in, we can define the lower and upper bounds. And we can do that for all the design variables that we like to vary as part of the design of experiments. We can then drag in the responses as well, following the same method, and specify the maximum number of runs for this design of experiments. Once we have the setup finalized, we can save it as a favorite in case we'd like to replicate it or rerun in the future. After that, it's as simple as pressing run, and the DOE tool will take care of running the workflow in a systematic way following its own predefined logic. Finally, we can save the results as its own standalone file that can be opened and revisited later. Now that we ran the DOE and generated the data, we can use it to perform sensitivity analysis. For that, we use the variable importance plot, which is a way to determine which variables have the greatest effect on responses, how the input variables affect each response, and it's used for simplifying formulation of future trade studies. The variable importance plot displays which variables affect a given response and how great of that effect it is, whether it's negative and positive correlation as well. It can use different statistical methods to generate the plot. The summary version of this plot can be used to display the effects of the same design variable on multiple responses. As part of the design exploration portion of MDAO, we're going to be focusing on a smaller subset of the design space. To get there, we're going to be using the parallel coordinates plot, which is used for narrowing down alternatives, represented by polylines, as can be seen in this image, as well as identifying trends of good design thanks to finding promising regions within the design space. The end goal is to be left with the few feasible options that satisfy all the requirements, and then use the plot to identify trends between them. For example, what the values are for the design variables, represented by where the polylines cross each one of those vertical axes, and then also how they perform in terms of your objectives. Once you have all of that identified, you can use that information to effectively narrow down the search scope of future trade studies. Moving on to the demonstration portion of design exploration, let's first generate a variable importance summary plot using the data generated from the screening DOE. This plot can be used for identifying how the different design variables affect each one of the responses, whether they have a positive or negative correlation, or how great an effect they have. As you can see here, as we switch between the different design variables, the same design variable is highlighted in the different plots. Design variables with very little to no effects can be eliminated from future trade studies in order to simplify them and lower execution times. The next step is to use the parallel coordinates plot to narrow down our options. The next step is to apply an objective, such as maximizing turbine power. Then we can go on to specifying the constraints on this design space. Constraints are another way of referring to the requirements of the project. Every time you specify a new constraint, more of the polylines turn gray. That is, they have become infeasible because they violate one or more of the requirements. We can choose to hide the infeasible designs and focus only on the ones that satisfy all the requirements. As you can see here, there are very few left. That is, this is a highly constrained design space, as are most engineering problems. The plot can then be reorganized in ways to help the engineer identify design trends. Unexpected results can then be further explored with additional plots, such as the 2D scatter plot that we're about to generate. The ModelCenter plots share the same constraints and objectives, making it easy to explore the same data in different views and formats. In this case, we'd like to further explore why we're getting such high stress values. If we look here, we have tower diameter versus tower base stress, and there are some outliers, close to 5,000 MPa. If we open one of these, we'll notice that the results are a combination of lower tower diameter and material thickness. So moving forward, we could raise the lower bound of both of these variables, and hopefully that should avoid this issue. Thanks to using the data generated from the screening DOE for design exploration, we have a well-understood design space, and we can afford to run a targeted DOE. A targeted DOE is meant as a follow-up to a screening DOE, for when you have a well-understood design space, and for when you have new design variable bounds, which will lead you to run a DOE over that newly discovered promising pocket or pockets of the design space to further investigate the region and obtain more feasible design options. To run the targeted DOE, we're going to be using the same tool as for the screening DOE, and the same favorites we had saved previously. This allows us to quickly update the settings and rerun this DOE with the targeted approach. So here we're updating the design variable bounds, which essentially means we're focusing on a smaller portion of the design space that we know has promising solutions. And since we know that there's more likely to be feasible points within a portion of the design space, we can afford to run additional runs, since we expect the design points within this pocket of design space to be of better quality and more likely to be feasible. Once we have that DOE finalized, we can start generating plots again using this data. In this case, we're going to go with the same plots as we did previously, just to show the contrast in the results. As you can see here, after applying the same objectives and constraints, we're left with a lot more options than we were before. And that's because we took into account what we learned previously and applied to this targeted DOE, so that this new set of data has more promising and feasible designs. We can then use a different type of plot to visualize the design space around the region in a different format, such as a 3D scatter plot. Here you can see that we can plot up to 6 variables at once. And this plot, once again, it shares the same constraints and objectives as the parallel coordinates plot. So far we ran a screening DOE and we used that data to learn about the design space. Then we took that information and ran a targeted DOE over a smaller portion of the design space. Now let's use that information that we got from the targeted DOE to find a good starting point for an optimization to come. For that, we're going to be using the prediction profiler plots, which are a type of manual design study that allows you to dynamically change inputs and visualize the predictive values of the outputs. It does so by using surrogate models behind the scenes, and it's best for visualizing the design space around optimal designs, which can be very useful depending on the optimization strategy you'd like to take. Starting with the prediction profiler XY plot. This plot shows a series of different views of the same design point. Each one of these views displays one of the design variables plotted on the x-axis against one of the response variables plotted on the y-axis. In red, we have the infeasible regions. If any one of these views is in the red zone, it means that the current design violates one or more requirements. The dots represent the current design point. In other words, it represents a slice of the design space of one input variable against one output variable. There is also a prediction profiler contour plot, which is essentially a sliced design space of 2 design variables. This plot allows for a much more detailed view of the design space by allowing the user to plot multiple requirements at once as different color-coded regions. On the other hand, the responses can be plotted as objective contour lines, such as the one seen here plotted in blue. These 2 plots can be used to explore, such as the one we found thanks to the screening DOE and design exploration plots, and obtain data for already using the targeted DOE. So let's take a look at how to use the targeted DOE data to generate these 2 plots and use them a manual design study that we can use to predict the values around the optimal design. Once we have generated all the different views, we can see here that the current design was already in the red. So we can move one of these dots down, which means lowering whatever design variable that is, while also changing and tweaking around with the other different views. So trying to get a better understanding of that smaller pocket of the design space and manually find a good solution. And the reason for that is When you go into an optimization, if you can provide it a starting point, you're basically giving that algorithm a head start. So it's going to arrive at the optimum solution much quicker and save you a ton of time and computational resources in the process. Going through these steps also allows the engineer to gain a better understanding of the targeted region of the design space. It prevents you from setting up the optimization incorrectly, such as using the wrong algorithm type or method for that particular use case, or design space shape and conditions. By the end of these steps, we found a design point that's feasible and gives us good results. So now let's go over the process again. So far, we ran a screening DOE. We used that for design space exploration, which helped us find a smaller region of the design space with promising solutions, which we then ran a targeted DOE over and used that information, that data, to find a good starting point. Now let's use that starting point as part of an optimization over a wind turbine design. When it comes to algorithm types, ModelCenter boasts a wide selection, such as local search or global search strategies, gradient-based or genetic-based algorithms, and more. When in doubt, you can use our wizard to help you choose which is best for your use case. Or even easier, you can go with our smart algorithm, the Nuisys Navirun, which is parameter-free and self-guided. From a user's perspective, all you have to do is say how many function evaluations or runs you can afford to wait for, and press run. The algorithm takes care of the rest. By figuring out what the best strategy is, such as figuring out whether it should be a genetic-based or gradient-based optimization, and then combining design exploration with global search and local search. So let's see how one of our users would go about setting up a single objective optimization. First, we launch the optimization tool from the Tools menu. Then we drag in our objective. In this case, it's going to be turbine power, and we'd like to maximize it. Next, we do the constraint, or one of our requirements. In this case, power coefficient, and we set a lower bound of 0.4. Then we can do the same for any additional number of requirements, such as cost per megawatt and tower-based stress. Next, we do the design variables. So those are the input values or input parameters that the algorithm is going to be varying through between a lower and upper bound in order to find the best combination that gives you, in this case, a maximized turbine power. Once we have specified the bounds we found through design exploration, we can go on to selecting the algorithm. In this case, Nuisys Navirun. Just like any other trade study in ModelCenter, you can save the predefined setup as a favorite. Once you press run, the algorithm is going to be taking care of varying the workflow at those predefined design variables and bounds, and plot the results along the way. So in gray we have the infeasible designs, and in blue the feasible ones. Highlighted with the red arrow, we have our starting point. So we start around 3.4 megawatts for turbine power. At the end of the optimization, we get a maximized design that gives us 4.6 megawatts for turbine power. So that's about a 35% improvement from the design that we manually found using the prediction profile it plots. While the optimization is still running, or at the end of it, such as this case, we can launch the View Output dialog, which allows the user to see additional information such as a summary of the problem definition and best design results. Since this was a single objective optimization, the best design values were automatically sent back to the workflow. So far, we went through the entire design exploration process of generating the data first, using some plots to find a targeted region, identifying a good starting position, running an optimization over a wind turbine design. Now we can finally switch our focus to optimizing the entire wind farm. When it comes to the wind farm problem definition, we have two objectives: maximizing total power, minimizing break-even time. We also have 3 requirements and different types of design variables. When it comes to the design variables, we have a mixed design space of continuous and discrete variables. If you're not familiar with the terminology, discrete variables are variables that can only take a list of predefined values, such as the number of turbines, generator type, or location, as opposed to continuous variables that can take any values between a lower and upper bound. This directly impacts the type of optimization that you can run. Another differing factor here is that we have more than one objective, so it's a multi-objective optimization. That means that the solution to this problem is going to be a set of designs, also called the Pareto front, which are the best bang for your buck designs when it comes to comparing them to the other solutions out there. In most cases, multi-objective optimizations have conflicting objectives, such as increasing performance while minimizing costs. That leads to this range of solutions that you can go with the minimum costs while also getting lower performance, or getting higher performance, which comes at a price. So at the end of this optimization, the engineers presented with a range of solutions, and then it's up to them to figure out what's best for the use case, and exercise their engineering judgment to answer questions such as how much money should be invested and whether it's worth it or not. Let's see how that works in practice. So we launched the same optimization tool, but in this case we're going to be loading up a predefined favorite with the optimization setup ready to go. As you can see, we have the two objectives, the constraints are defined, and then we have the discrete variables here such as generator type, which is a drop down, same for location, and then number of turbines. These variables can only take a predefined list of values. In addition to the discrete variables, we also have blade pitch, which can take any values between 0 and 15 degrees. Moving on to the algorithm portion of it, we can tweak its settings and determine how many Pareto points you'd like the algorithm to find. That is, how many of those best designs you'd like to have in order to compare and decide which is best given your own use case. Once you press run and the optimization starts, a 2D plot is automatically generated and starts plotting the results of the two objectives against each other. As more and more results come in, the plot starts to form a curved shape. This curved shape is dictated by the requirements that you have defined in the optimization. And along its edge is where the Pareto points usually lie. We can choose to highlight the Pareto points so we can better identify them against the rest of the results. Alternatively, we can choose to display only the Pareto points. We can also expand the details of individual design points and customize the plot to better visualize the different alternatives that you have. Finally, through the View Output dialog, you can see the individual Pareto points under the Best Designs tab, and by switching to the Pareto Chart tab, you can generate a sub-dataset containing only the Pareto points that can in turn be used for post-processing. From here on, it's up to the engineer leading the project to decide which one of these is best for their use case. In conclusion, MDAO is not a tool, it is a process in which certain best practices should be followed. ModelCenter gives you the framework to bring the multiple disciplines together into a unified workflow, which can then be used for analysis and optimization using our design exploration suite of several different plotting techniques, as well as our extensive library of optimization algorithms. The process demonstrated in this example is generic enough that can be applied to any engineering problem, and highlights only some of the best practices. They are covered in more detail as part of our training offerings. This concludes this presentation. Thank you for your time.
All right, thank you very much. I'd like to just pause for a minute and see if there are any questions. There was a lot of information that was covered in that video. Hopefully everybody's kind of awake and been thinking through what you saw. Are there any questions out there? Give it just a minute here. If you have a question, I think you can unmute or just put it in the Q&A.
Quick question, Tony. Again, this is Tom Treffner.
Hi, Tom.
Totally fascinating and amazing what you can do quickly now using these automation tools to explore a design space. So my question is to do with unusual cases in the sense of as you're exploring, it's like you might say it's not a non-linear exploration space. In other words, some design element that suddenly goes, in a non-linear fashion, and even more so interactions. How do you deal with that?
Scott, you want to jump in on this one?
Yeah, Tom, can you hear me?
Yeah, we can hear you, Scott.
Barely, yeah.
Okay, very good. Yeah, so your question, Tom, was regarding how do you deal with nonlinearities?
Well, nonlinearities in terms of the design space you're exploring. Like, it seemed to me that if you're looking for the best, shape of a blade for a windmill, then the presumption is that as you go through the analysis in an automated fashion, it's following a smooth curve in terms of a design space, you might say. Are there real world situations where that isn't happening and suddenly it kind of just blows up, or it misses some really nice solution that can't be dealt with for some reason?
Yeah, so it's certainly possible that could happen, but we're not making any kind of assumptions about assuming things are linear when they're not. So whatever data comes out of the analysis, or whether it's nonlinear or linear, that's taken into account. There's another question here about the screening DOE, and that takes the underlying nonlinear response is taken into account when selecting where to run the design. And everything you see here, we're not making any assumptions about what the underlying design space or the underlying properties look like.
Yeah, I'd like to just add a piece to that. If you look at this, as you watch this video, this video highlights best practices, and a piece of that is doing things like DOEs and things like that up early, understand the sensitivity of of each of the variables and how they're correlated. So I think if you had a highly nonlinear event that occurred, you quickly find those early in your design, and then understand whether how to go about bounding that if it needs to be bounded. And then
okay.
ultimately, as you push forward into your optimizations and things, you'd understand, do I need to put a range on that, or is it going to basically leak away my whole, realistic boundaries?
Right. I mean, once again, totally amazing. And thanks for the answer.
Oh, no worries. Is there any other questions that came up?
Yes, I have a question. It's been a long time since I've worked in aerospace, but in the past, when we did aerospace, we would set up experiments and we would try things, and we do a lot of working around with I'll say tiger teams for lack of a better word, possible approaches. And then process of doing that, we devise tests and we devise empirical data. But in this video, I don't see any evidence whatsoever. It's like you have all the models preset, and my personal experience has been that that's how people die.
Yeah, certainly.
You have to validate the process, the beginning part of the process, and you have to validate every step of the algorithms. How do you do that?
Yeah, that's an absolute truth there. We would never say do this without doing testing. But what we've discovered in the last, maybe 10 to 20 years, what a lot of engineers, especially in the analysis world, are doing is they will create their models, and then they use a tool like ModelCenter to actually understand those sensitivities, and then utilize that in reference to correlation against test. So perhaps there's material properties that they believe are within a range. They go out and do tests, and they can do a single test or multiple tests, and then come back in and say, all right, are we within range on the material properties and how it should behave? Ultimately, as I mentioned earlier, when you talk about this invention versus innovation, most companies are risk averse. So what they will do is they will take and move things forward a little bit at a time. So with that, I mean, they're ultimately, especially with analysis, more and more coming to the foreground of how solutions are being done and less test. What they're doing is they're doing a lot of correlation up front to understand against test how the analysis works. And then as they progress that, they'll begin to move it more and more into the foreground.
Well, perhaps in your video, what would make people like me happy is if you had 5 minutes of the video explained, okay, we've got a new project, we're putting stuff together, these are the ideas the team has put together, and this is with the empirical data we've produced, and how all that first part gets done. My concern, and I think it's a really serious one, is how many of us know actually how to use PERT? Well, my generation, we all know how to use PERT, but then Microsoft came along with Microsoft Project, And a great many people started just throwing stuff into Microsoft Project, thinking that would solve their project management issues. And we had all kinds of horrible things happen because of that. People couldn't handle schedules, budget, nothing seemed to work.
Right.
Because they forgot about the first part of all this, where you establish requirements and you come up with some basis of what you put into your models.
Well, it's great that you're asking these questions, because the second part of this presentation is actually around taking system requirements and tying them directly to analytical and test-based solutions through ModelCenter. And how do you go about doing validation against that systems engineering solution to make sure that as you're looking at systems and systems of systems, how are they going to integrate together and understand, are they validated? You know, are we actually meeting those requirements? And as complex as systems have become, which, you know, anything from a cell phone all the way up to an aircraft or a space vehicle, you know, the complexity in them with the convergence of electromechanical systems has become significantly higher than it was, you know, even 5 years ago. So ultimately, that's a good segue for what we're going to show here in a little bit.
Okay, I'm still not convinced.
Still skeptical. I understand.
And the reason is we count on. I know, like, Boeing is risk adverse, but 380 people are dead because they had a single point of failure and they didn't do the basic things right. So that's not a good sales pitch to say, well, Boeing uses this sort of stuff. But more and more, there's pressure to do really innovative things. Mm-hmm. You know, electrically powered aircraft, helicopters using motors, aircraft that can, take advantage of aerodynamic conditions on Mars, which I find, like a parachute on Mars, I find extremely humorous, but that's just me. So how does this fit in where you have innovation instead of just slight improvements?
Yeah, I guess if you look at the alternative, you can, with as complex as systems are becoming, with literally thousands and thousands of lines of software in them, how do you go about, or it could be millions of lines of software, how do you go about testing that? You'd run out of days in a week, or years and years would take before you could put an aircraft in the air. So essentially you have to do some form of virtual testing to get past a certain point, and then go through the process of doing correlations against those analysis pieces and ultimately test to the extreme cases. So I think you're not going to catch everything. You do as best as you can to catch everything. And even as a test engineer, I can't imagine you would test everything and be able to catch everything, but you do your best.
Well, you raise software as an issue, and the complexity of software has always been a huge problem. But that also is based off of correct design assumptions, coding requirements,
absolutely
correct requirements in engineering analysis, which nothing you've described would touch any of that. The statistical probability of failures in software is pretty interesting, because most places don't check every possible path. And yet they use things like Linux that has 30 million lines of code in it.
Right.
Well, none of that's addressed here.
Well, when you have
expected to.
Well, we didn't think to put that in this particular presentation, but we do have a very significant team that goes through our code anyway and does a lot of work with trying to test it and beat it up in every form possible to make it robust. And then it also goes out to customers as beta, where they can go through that process as well. So
Tony, Bill, this is Scott. If I could make a comment, probably we should think about how we present this to an audience such as this. But nobody here believes that this is the only thing you do when you design an aircraft or any complex system. This is just one tool that can be used to make the design process go faster. And you talk about innovation, ways to ask what if questions using the computer, but nobody should ever only do computer-based design and assume it's correct. So I think
that first step's important, don't you think? Where we talk about the rules, how this would fit into a more traditional development methodology. Let's put it that way. Because my concern, which is I think quite based off of lots of years of experience, is that as soon as we automate things, then people find ways to shortcut them. And there's not sufficient emphasis on solid design rules and things like that. And determining if something, I'll pick on Boeing, single point of failure. Who in aerospace would even consider a solution as a single point of failure? See?
Yeah, well, I mean, it's the same thing with, 25 years ago when Ford was primarily doing tests and they had a rollover incident that occurred. It was a combination of many different things that caused that rollover. Now, could that have, if they would have had a solution like a ModelCenter, maybe that could have been found earlier, or maybe it could have been, or maybe it was missed. Who knows? But this definitely as a tool allows engineers and organizations to basically try a lot more different virtual tests than they could ever on a design test.
So maybe what, I don't mean to be critical, but maybe the positive thing is your presentation, the first part of it is, where does this fit into a quality-oriented development effort where you have mission critical, you have lives at stake or things like that? Where do you fit this in? And
so go ahead.
And that would be part of your presentation.
Yeah, we could definitely do that. Just to answer that question, though, we see a lot of this being utilized in the early portions of design when they're in the conceptual space, trying to decide, do we go left or right with the design? But more and more, this is flowing down into production and even operations. So there's a concept around digital mission engineering that ModelCenter is becoming heavily utilized in, which is how do you bring that physics as far forward as possible so that decisions can be made in an operational perspective. So that's a whole different topic altogether, but it fits basically within each organization differently, but every organization finds value.
Okay.
Okay. All right. Any more questions before we get on?
I think Randall has a question.
Okay.
Randall, you're welcome to speak out. You're unmuted. Ushiyama? Okay, if it doesn't, I'll read. Basically, he was asking how sensitive is the screening DOE when dealing with highly nonlinear systems with multiple possible good solutions?
Yeah, I can comment on that, Ken. This is Scott again. When running the DOE, there's always a trade-off between how many runs can you afford to run, to actually run. I mean, how many simulations can you afford to do, versus so that the more you can do, the better coverage you're going to have. But it costs time, etc., to run a simulation. So there's always a balance between how many can you run versus what kind of accuracy you need to get. And so when people who do DOEs are always trying to meet that balance, and they're trying to run enough simulations so that they can capture all the non-linearities in the design space. The particular DOE that was in the movie is an adaptive DOE that actually samples the underlying functions, and it tries to put more points in areas where there are interesting things happening. In other words, large curvatures or gradients, and so on. So it does its best to cover the design space in a limited number of runs. But it isn't always a balance, and it's always a tricky thing that you have to be really careful of.
Okay. Any other questions, or is okay? I'm gonna go ahead and progress on, and then if and we'll get to another spot where more questions can be asked. So let's look at some of the challenges. We kind of talked through a few already, but let's look at them a little bit deeper. So we polled customers to determine what the challenges are that they have in performing model-based engineering. And here's what we uncovered. Every engineer does things a little differently, falls into categories of quality and rework. We spend too much time looking for the right data, efficiency and rework. We spend too much time looking for, we do too much manual work, and that falls into quality and efficiency. We need easier access to high performance computing so that we can optimize our designs. Again, quality and efficiency. And finally, our engineers don't have time to learn new tools, and again, quality and efficiency. So at Phoenix, we recognize the solution to these problems is a cloud version of ModelCenter, also known as ModelCenter Cloud. When you expand the use of ModelCenter into a cloud environment, you raise the ability of your entire organization to take advantage of the work of your subject matter experts. Your SMEs become rock stars with the following. So how does this work? First, we provide your subject matter experts who build workflows to have better access to high performance computing. This includes the ability to click on any component within the workflow and designate where it runs. Finally, if the company or the organization decides they want to do this, we provide functionality for your subject matter experts to expose their workflow to any analyst in the organization that could benefit from the access to the subject matter expert's workflow. We call this methodology modeler analyst configuration, putting the workflow built by the experts in the hands of analysts that need the data to make holistic system level decisions from this information. This could be other subject matter experts that need your workflow. Perhaps it's an operations group, manufacturing, marketing, systems, etc. It's no longer is that information just trapped in a box. It's exposed, becomes more transparent and available to others to be able to essentially ask questions about this information and understand, is it the right information for this project? So also note that this cloud can come in many forms. Private clouds to run on your company's own high performance computers, things like Microsoft Azure, Amazon Web Services, and the Gov Cloud. We manage the workflow in every type of cloud type for every need. So let's review these challenges. If every engineer does things differently. Not anymore. This can access to common workflows. Check. Too much time looking for the right data. Not anymore. Data is at your fingertips in the cloud. Too much manual work by everyone on the organization. Nope, with the automation of integration of workflows in a cloud environment, they become available to everyone. So everyone can take the time to understand what this workflow is about, and essentially, as has been mentioned in the past, kind of raise the bar for everyone. Access to HPC to run your workflows, and finally, a ModelCenter Cloud interface which you will shortly see how this is utilized. So let's dive a little deeper into this ModelCenter Cloud components. First are the components for your modeler. This is ModelCenter on the desktop with a publish button that allows the modeler to publish a workflow into a ModelCenter Cloud server. It also provides the modeler direct access to the HPC. Then there is the graphical web interface for the analyst. This allows the analyst to call up a workflow, modify input variables, and run a single workflow or design of experiments to explore the design. And finally, not to leave out the system administrators, we provide tools for them to monitor running workflows. This will not be covered today. So let's start with the modeler and from this and bring it back to that earlier demonstration of the wind turbine. How would this look in ModelCenter Cloud? And let's take advantage of the HPC integration with ModelCenter with that modeler analyst methodology. So as shown earlier, we start with the turbine models, and we'll put them into a wind farm. In this case, the positions of the turbines could disrupt the power generated by any one turbine. So we'd want to position the turbines and modify the turbines to ensure that they create maximum power for the lowest cost. Before I show you the demonstration, let me highlight a few items, starting with the subject matter expert, AKA the modeler, who built the original wind turbine workflow. He will first want to publish the workflow to the ModelCenter Cloud server. This is done simply by clicking a few buttons. Once that workflow is uploaded to the ModelCenter Cloud, the modeler will then run through a set of checks to ensure that everything is running. Remember, eventually an analyst or non-subject matter expert may want to run this workflow to make decisions. So essentially, let's harden that workflow, or let's make it more robust so that they are not able to fall into traps or use it incorrectly. So as the workflow is executing, you can monitor the progress and debug issues. For example, if a value goes out of range. And we're going to show you an example within this workflow of how we purposefully put in a bad value so that the builder can actually go in and make changes to harden that workflow. So I'm going to go ahead and start the video here and speak to it. And Scott, feel free to jump in as you see necessary. All right, so to start, we're looking at the workflow that was essentially created earlier with the wind turbine. And you can see now that there's certain components of it that are actually running in a cloud configuration on a server. And we're going to dig in a little bit deeper and show a few more of those server components. So in this case, there are specific components within this workflow that are running locally, and some of them that are running on the cloud. So it's a hybrid approach while this modeler is still going through those tests. So we hit run, and you can see the workflows running. And then you can go through and check values to make sure that they're within parameter, within range that you're expecting. So as mentioned, we're going to go ahead and put a value outside of range, which is we moved the diameter from 40 to 100. And now we're going to publish this workflow to the cloud. So on the left side are a set of files that reside locally, and also which ones we want to push to the cloud. So we can go through and select all the values that you want to put into the cloud environment, and perhaps there's models that are still being worked that you want to keep close in your own desktop, but still be able to run as your testing cloud configuration. On the right-hand side, there's a lot of values shown there. It's very likely a engineer doesn't want to expose all the values to an analyst. Otherwise, you could possibly run the chance of him putting in a bad value. So you expose only the values that a person, that the modeler would want the analyst to look at. Also, we're hitting the auto publish button. So what that means is that we're going to go ahead and publish this workflow, but because we hit that auto publish button, now if we go back and make changes to that workflow, it'll automatically update to the cloud. So now we're going to look at the cloud side of this workflow. So we're going to log in through a web interface. And you can see we've been doing a bit of testing on this particular wind farm. So we're going to open up the wind farm last version that we utilized. So we go and select that wind farm. And basically the workflow associated with that wind farm. And all the components are listed there. So on the left side are input values, and you can see they have units if units were specified in the workflow. And on the right side are values and units associated with the output. One question that always comes up is, do you have to take it out to so many significant digits? And the answer is no. We can actually format that differently. Now we're going to go through and create a job on a specific cluster, or high performance computing cluster, with a specific queue that's available. And we're going to submit that job. Now, if you remember, we had actually put a value out of range. So it's very likely that this thing is going to crash, or at least cause a problem, which it does, it errors. And this is only for demonstration purposes or just to show you how it works. But ultimately, you can see that the one of the components is red. It's the one that failed. And the person can look at that workflow, hover over top of it, and actually it points them to where in that particular component it failed. So we go back to our workflow. Let's put it to a value that we know is going to work, kind of a high-low limit. Save that workflow, and because we hit that auto publish earlier, now it's going to push that automatically up to the workflow. I'm sorry, up to the cloud. We go down to our workflow. We go and view it again. And you can see the updated value is now at 40. We're going to change and recreate a new run. Select our cluster in our queue, and then hit submit job. That workflow is now going to go off and run again. And ideally, in this particular operation is going to finish successfully, which it has. So we now know that we have a successful workflow, and we can check the values to make sure it behaved properly. Okay. So as a review, if a failure does occur, the subject matter expert can see the components that failed and work directly through ModelCenter and correct any errors found, or coach the analyst on the best practices of the workflow. So for example, let's say that there is a component that fails that the analyst doesn't necessarily recognize, or the modeler doesn't recognize, or the analyst, as he's hardening the model, recognizes something's out of place or not working properly. They'll know exactly what component was done, and on a very complex workflow that might have many people involved, they can find out who, from the metadata within the component, who actually created that component, and to go talk to that specific subject matter experts. So you saw how we clicked on the publish button to send the workflow to ModelCenter Cloud. And as an option is available that you can make the changes to the workflow, these can automatically be saved into the cloud. A lot of times when we work with customers, they typically will have a development side workflow server as well as a production side workflow server. The development server would be interacted with in the way we just described, and then only once that workflow has been kind of hardened or created as a robust workflow, at that point it's moved across to a production server for use by analysts. And as you saw, you can actually create a library of workflows over time. So now that workflow has been published in the cloud, everyone can utilize the expert workflow. Democratization of the workflows for anyone's use with expert oversight. As more expert workflows become available, your organization will become more and more efficient in its approach to how it models. Essentially, the question that was asked earlier about, how do you ensure that these workflows become, are usable and usable by many, and perhaps are bug-free. It in many ways is done through a hive mentality of other people creating that workflow and utilizing that workflow over and over again to find the errors. So essentially, it raises the bar for everyone. So let's change hats now, and now I'm an analyst. And analysts are people in your organization who could benefit from the use of this automated workflow to make decisions within the organization, or perhaps they interact with your customer directly as these workflows are being run. This could be things, again, like marketing, operations, management, sales within the organization. So with ModelCenter Cloud, they can benefit from the simulation expertise of your subject matter expert without being an expert. And we have customers that do this as they're going out in the field to do things perhaps with a wind farm or with other tools that they create where they have to go and they don't know about the parameters until they're on site to be able to run the analysis. So to preview the output, the analyst can perform design of experience based on the parameters that need for the specific project via the web interface. ModelCenter Cloud's visualization and plotting infrastructure, for example, the analyst could use 3D scatter plots with filters to understand the relationship of the performance versus cost of your company's products. The Pareto front, to find the best combination of performance parameters for your design, where you need to make a decision based on your customer's needs. Parallel coordinate plots. In this plot, each vertical line is a performance metric and the horizontal lines are individual lines. This plot can give you trends for your good designs. Or if you like simple old 2D plots for honing on a specific feature. Very powerful tools. So let's examine the ModelCenter Cloud from the analyst point of view. The analyst has already logged into ModelCenter Cloud. And at this point, they're going to that workflow that was created earlier. And they're going to go about running this particular workflow on a cluster with a specific compute nodes. But in this case, they're going to switch to a design of experiments. So they're actually going to set up a design of experiments to explore a set of parameters that are viable for the location that they're currently looking at for this wind turbine. So they set in a high-low values of the that are available within the for each of these values. And on top of that, the expert, the subject matter expert, has already put high-low values ranges within this. So you cannot play this without the above or below those high or low values, so that you can't go out of spec. And then you pick the particular outputs that you want to track and trace. And then you can determine how many factorials you'd like to utilize. More factorials means longer runs, potentially exponentially. So let's go ahead and run that workflow, that design of experiments. So each column is the set of inputs and outputs for each analysis that's being run. The model or the workflow is currently executing, but even while it's running, you can begin to look at results. So you can see if you're within boundaries that you're trying to get to, or if you're actually tracing in a wrong direction for your particular use. So on the left side, you can see the different values and variables that are being created. The solution will tell you how long it has left to run. And then ultimately, you can go in and start looking at the many different design parameters that are plotting methods that are available within the ModelCenter Cloud solution. So we talked about parallel plots earlier. So let's go in and start looking at the results and setting various objectives based on the constraints that we may have locally for this particular wind turbine example. So you can see in this particular case, the turbine power went from roughly 4.3 up to 5, over 5 megawatts. And we're going to go and jump to, just to show we can jump through to other results. We're going to do a 3D scatter plot and review that. And again, this is the gives you the ability to look at approximately 6 to 8 different output variables at the same time, based on the XYZ coordinates of the plot, as well as color and size. And then we can go through and hide infeasible designs, so we can reduce the number of available plots. And because all the filters, as you create these plots, the filters are maintained, you can then move between the different ways of displaying the information to dive deeper into each one. And in this case, we're finding various values where we can actually make a decision against it in terms of cost versus turbine power. We can go in and highlight the Pareto front that we mentioned earlier in the previous video. And you can see this particular value gives you a 0.336, it looks like, gives you high value versus or high turbine power versus cost. Ultimately, we can save that design or save all the data in design, but specifically we can save a specific design so that we can then utilize that later, or perhaps years down the road as the part is manufactured and other things that occur in the process. So in summary of this section, we access ModelCenter workflows from the cloud. We used web browser, no need for ModelCenter install, no ModelCenter expertise or other modeling expertise needed. The interface is easy to use, accessible from a computer or tablet on things like Chrome, Edge, etc. Different web browsers. Help more engineers get the benefit of standardized, automated, integrated workflows that follow best practices and spread the benefit of ModelCenter to a larger audience so that they can design the best practices, best products. So essentially open up the door to doing this MDAO application to more people. And then ultimately, we allows you to help your audience interact with your design through a design review rather than just showing static charts. So that as you're doing your design review, you can bring up these type of tools and have your customer ask you questions about what do you want to do? Why are you doing it this way versus another way? So we also looked at a few of the plots from ModelCenter on ModelCenter Cloud. We ran a DOE from ModelCenter to speed up execution by executing on multiple compute nodes. And behind the scenes, we can make use of ModelCenter's compute infrastructure the company has to execute the workflows. These can be ad hoc computers or dedicated clusters and clouds. And then we utilize the tools to also make better decisions. Your design selections can be saved in ModelCenter Cloud, so that if you come back to them 6 months later, you can understand why you made the decisions you made. In fact, because the Turbine example is now moved to a cloud environment with more people being able to access and run the solution, and because the solution runs faster with HPC integration versus just a desktop solution, the Turbine power has increased from 4 megawatts to 5.3. So to summarize our MDAO and ModelCenter Cloud solution, we showed how expert modelers, builders, can build a workflow and solution from the desktop. Then we showed how they can publish it, to the workflow to the cloud to take advantage of their HPC configurations. Then we showed how an analyst can utilize the expert modeler's workflow for the purposes to make decisions on the product while saving the workflow and the key inputs and outputs of the workflow, making the workflow archived and repeatable. So again, I'm going to pause for just a few minutes to answer a few questions. Do we have any questions out there?
Everyone, you're welcome to everyone unmute yourself and speak out your question, or you can type in Q&A. So while we're waiting for a question, I do have a question. So you're saying that so the software itself is installed on your cloud, or you can also install it on companies, the cloud as well.
Yeah. So let me answer that one. So basically, we don't host any cloud servers on our hardware. It's primarily we want customers to utilize it on their solutions or in one of the public clouds like an AWS or a Microsoft Azure. Essentially utilize the clouds that are available today commercially. So we don't provide a service in terms of hosting clouds at our company.
Okay, so for example, the first speaker, Mr. Dan Adamo, say he's an individual, a consultant. So it's any smaller version if we want to use it. So all he has to do is to pay and subscribe to the AWS or Azure, or is something that can install on his computer.
So ModelCenter itself, if you're just looking to build, like what Dan was showing earlier, if he wanted to actually just work on his work, he could do it on a laptop or a local computer that he has. However, he could put it onto AWS as well if he wanted to expose his work to others. And
yeah, because
and allow them to actually play around with his designs.
Yeah, actually, if you probably also realize his project could potentially become a good project utilizing your product. Actually, those water tank, those fuel, those things. I think we.
Yeah, I can definitely draw a direct line. I was doing that the whole time he was he was presenting. I was like, this is a great segue for the work that I'm about to show.
Exactly. It's a good.
Looks like there's another question that came up. So from Randall, says, how long does it take to become a proficient in these tools? How long does it take to become an expert in these tools? That's another great question. Thank you very much, Randall. So we offer, for ModelCenter itself, we offer a 2-day class that provides you with access to the software for up to 2 months and allows you to actually utilize the software. We teach you how to do all the workflow creation. So essentially the automation, the integration, and the iteration of the workflow. And then we, a lot of times we'll work with customers on a part 2 of the class would actually be to do things like work with them how to go about using some of the algorithms that I showed. And that's called our ModelCenter Explorer component. And then finally, the next section of this presentation is going to go into what's called MBSE. We have an MBSE integration for systems engineering. We offer a class in MBSE where we teach folks how to do that. And because of COVID, we moved all our trainings to online, and they're either online self-paced or online instructor-led. So anyone can get started pretty quickly. So to become proficient at the tools, it may take a few months to get your own workflow up and running. We have customers that take to it pretty quickly and get things up and running within a few days to a week. We have others, because of the complexity of their workflow that they're trying to do, it might take them a few months. So it's really just dependent on how much you know about your own workflow and the components within your workflow, and frankly, if you've built them to be reusable, because a key component of this is the ability to with any simulation that you're utilizing, that you've built it in a way that it can actually be parameterized or perhaps be driven to make change to it. So hopefully that helps.
Yes, everyone, you are welcome to unmute yourself and speak out your question. So while we're waiting, I have another question.
Okay.
So you mentioned about this, the subject matter expert and the model, for example, the windmill, those turbine engine. So
Yep.
for example, now the subject matter expert, they figure out they have some their own physical model. They decided, okay, say for example, now the operating temperature, is a factor, for the turbine in the windmill. So they would like to add this into this model. So is it something they can do easily themselves to click an icon and build in their model, or you need your help, to provide a new icon or component for their new model?
Yeah, that's a fantastic question, Ken. That comes up quite often. So the way our philosophy at Phoenix Integration is we basically provide you the tools to integrate any simulation tool into a workflow. So if it's a tool that you perhaps don't see within a list of tools that we have already plugins for, we teach you how to create that integrate that into a workflow, automate and integrate it into a workflow. So if you do have a subject matter expert, as you mentioned, that is very good with ModelCenter, then most likely they can take the tool set from the thermal analysis guy, for example, that you mentioned, and help them with integrating. Or perhaps that thermal analysis guy can go to class and we teach them how to integrate. But the concept of integrating different disciplines together, that is exactly what ModelCenter was built for. And those disciplines don't all have to reside on the same computer. They can reside anywhere within the organization. We have a technology within ModelCenter called remote execution, which allows an engineer to build a workflow on their desktop that basically replicates the process that they go through to do a form of analysis that can then be accessed from anyone else within their organization that they allow. So if I'm a mechanical engineer and I need a thermal analysis brought over from the thermal guy, or perhaps an aerodynamicist has a piece of analysis that I need to be able to make loads or whatever it is that I'm looking for, I can actually take a piece of their workflow and bring it into my workflow. We also have the concept of surrogate models, which means that you can take models and replace them with tabular data, and ModelCenter can easily do that. It can take a workflow and run that workflow, hundreds or thousands of times to create that multidimensional results that can then be instrumented into a workflow. So if you have something like a CFD analysis or something that could possibly be long running, you can pre-run all those and then bring them in on a variation, on another workflow as part of that workflow. And you can do things like switching and put if-then statements. So if the results can be interpolated off the response surface that's created as part of a surrogate model, it can pull that information off, or it can go and run the CFD analysis for each run.
Yeah, that's why I asked this because, for example, in Mr. Adams' presentation, he talked about nuclear thermal, engine, nuclear thermal propulsion, and there's been, heavily, intensive development right now. So the model could change, as it goes. So the other thing is, if when you mentioned about the demo, if it's something is more the time evolving, saying there is a capability of making some kind of movie or video as for demo, to have this capability in your software or system. Not just the
I'll show you some stuff here in just a minute, where say Northrop Grumman will actually pull in CAD information, and CAD models are being updated as their as parameters are being changed. You'll see that in just a minute.
Okay, I think Scott answered some questions for BO, and I don't know if we see we click answer. I think Scott typed in a question from BO,
okay,
and also I think another question from Jim, Mr. Robinson.
Okay.
Did you see it? Did you? If you click,
I click on the Q&A.
there's an answer in the middle. There's an answer question.
Okay.
Yeah, Tony, there were two questions that I answered. One having to do what MBSE systems we integrate with.
Oh, okay, I see.
And the answer to that, if anyone else is curious, is Magic Draw / Cameo, Rhapsody, Genesis, and Windchill Modeler is what we have picked today. Antonio will go into more detail with that in the last part of the call. So we do not integrate with Capella, but we'll consider it.
Okay. Yeah, sorry, I was just getting used to this Zoom interface a little bit. We use a different tool at Phoenix. I see your answers now, Scott.
Okay, yeah, the other question that I answered had to do with, there was a question if it's possible to add custom optimization algorithms. The answer to that is yes. We have a standard SDK software development kit for adding your own algorithms. And we have another number of customers who do that.
Okay. How are we doing on time, Ken? Are we still okay?
Yeah, still okay. You have all the time till 2:15.
Okay, excellent. Any more questions that we want to cover, or do we want to push forward?
Quick question, if I could. This is Tom Treffner.
Hi, Tom.
Great presentation so far. I particularly like that video at the beginning from Noesis. Went through all that, showing how that works. As I'm thinking about this, a couple of words you've mentioned really stimulate some thoughts. Like you talked about the group that goes through using the tools really essentially come up with like a high validation and best practices, and come through with things that you would normally do in a traditional engineering process, but now accelerated, or really I think of the word as amplified. This tool is like an amplifier for the engineering process.
Absolutely.
So where it leads me to thinking then is back to that early 15-minute video. There was a couple of steps in there, for example, using the screening DOE, and then the prediction profiles, where it was helpful if the engineer was able to, having used the earlier parts of the analysis, then find where to go next, you might say, in the available design space to accelerate, the next steps. So I was thinking, at a higher level, almost like a meta level of this tool, maybe it's a future kind of thing. It seems like the tool, ModelCenter with Noesis, could be almost monitoring the whole process, looking for those sweet spots that nobody can really spot individually, because you're all working in your own particular SME area or your own specialty. But the tool, in a larger sense, and I don't want to get into too much science fiction thinking, but it would seem to me it could start spotting things that are really meta level accelerators to jump to good stuff.
Well,
it's almost like if you think of a traditional engineer who, over his career, he gets a feel for his area. He becomes he has an intuition, but only having looked at a lot of stuff. Well, really, that's what ModelCenter could eventually provide, it seems to me.
Yeah, so there's two fantastic concepts you're talking about there, and one of them is the ability to actually get smarter about the products that you're creating, and I used to have a presentation that I would do where essentially, if you think about all the different branches you could go down when you're doing an analysis, you could go down many different branches, but ultimately you decide on one that you want to utilize. But all these others actually result in the wisdom that you created around that product. It's understanding. Right. It's a key level of understanding and wisdom, so that for this project I didn't want to go that way, but perhaps on the next one there's a need to go down that path, and so you can, as an expert engineer, you become better and better at that.
It's like knowledge capture.
That's right. That's exactly right. And as you progress the whole, I'll jokingly call it the hive, but as you progress your whole engineering organization, everyone can begin to expand their experiences much quicker. And I always talk about, engineers, a lot of times you don't go to school necessarily to spend your whole day building models. You go to school to be able to make decisions against those models, and the experience that you gain from, understanding models and ultimately making decisions against them is the value that you bring to your organization. It's not necessarily just pushing buttons on a computer to make a model. It's utilizing that model over and over again. And if you look at, unfortunately, the way a lot of organizations work in today's world that aren't using a tool like ModelCenter, they typically go from into a PDR, a CDR, and perhaps a final delivery. So what I've what I've seen over and over again, and you can ask just about any engineer that works in aerospace or any other space, is that typically they're going to build models. They're going to build a model that that models a specific feature or function that they're trying to understand. Do we meet this requirement, perhaps? And then what happens is that the charge number runs out. They ask the engineer for his final answer, even though he might have only had an opportunity to do one run on that analysis. He gives them the answer, and they say, go work on another project. When in fact, you really want to look at a cloud of answers and understand what's the best piece to pick out of that, and have that trade space available to you to make those decisions.
It's it sounds like you have a very cool product. But one question that comes to mind, because I'm involved in cybersecurity,
Mhm.
and the question is, how do we assert design rules? And I'll pick on Boeing because that's fun today. A lot of my friends came from Boeing.
Okay.
Is, for instance, we used to have fishbone diagrams and
Yep.
single point of failure diagrams. What happens if this happens and this happens? Is it possible to assert design rules with your system?
Scott, you want to tackle this one? Or do you want me to tackle it? Hopefully I lose Scott.
need
Oh, there we
to unmute myself here.
go. Yeah.
Not explicitly, it's not, but when you're doing a multidisciplinary analysis, like Tony showed in the first part of the presentation, you can write rules that the entire system essentially they're constraints. The entire system has to obey those rules, or it's not considered to be a feasible design.
Well, one of the obvious example is fishbone analysis. Single point of failure, multiple point of failure type rules. In the cyber world, you might have encryption, or you might have multiple, backup channels or something like that for communications. That'd be an awesome, because the way I see your product, which is kind of interesting, is once you build the models through hard experience, then as things change, you have an engine blow up in the test chamber, for instance, and you change things, then it's really easy to go through all of your work and all of your previous systems and go, oh, look, we got something here. Oh, we got something here that we need to address.
Mm-hmm.
And I see that's potentially, I don't know if your system would allow you to do that, but I see that as a huge advantage if you could do that.
Well,
hey, Bill, can I jump in? Can I jump in here, Bill? This is Tom. Just going back to my comment before yours, Bill. The word I would come up with and add it into your tool, no problem, Tony and Scott, model-based lessons learned.
Mm-hmm.
So what Bill was saying would be like a way to have smart lessons learned applied as appropriate.
Yeah, I mean, so one of the things that we look at trade spaces, right? And we only focus this time on the Pareto plots, right? The pieces that we expect to be the best solutions. But if you look at the way those are built, typically they create what's called an ant. You can look at them as, I always jokingly call them an anthill plot, and there's outliers that occur in those plots, and those outliers perhaps can fall outside the boundaries of solutions. And it could be that it's a combination of variables that cause those outliers. And it might be that you want to go focus in on those outliers as opposed to just the Pareto component. And we didn't cover it today, but there's a whole piece of ModelCenter that deals with doing probabilistics. So, when you optimize, you're basically taking on a bunch of assumptions and you're trying to optimize against those assumptions. Well, you can
My question is slightly different than that. So let's say I'm a large corporation that makes turbines, because I used to work on turbines, fuel control for turbines. And you've got 50 products out there and you've got 100 customers because you heavily research your turbines in the supercomputer center, which is what we did. Mm-hmm. And you make sure that they're all, the best of class when they're designed, right? Mm-hmm. But now let's say time moves forward and you realize that alloy you used or in a fuselage, that high-tech plastic that you're using, it's got micro cracks, and you go, oh, our models were wrong. Oh, now the cool thing I see, and I don't know if you can do that, is once you discover that, you're liable for all that anyway. Mm-hmm. But once you discover that you have a deficiency in some material that you're using, you could rerun all of your designs.
Yeah,
And
I
where
mean,
that was a problem, you'd get a red flag and you'd say, okay, these are the people we have to talk to right away. They're using MCAST. I'll pick on MCAST. They're using whatever, right?
right.
And then you can notify them, and you can put in place as a management issue what you have to do to protect your company by protecting them.
So exactly what you're talking about happened back in 2018 when a specific, not going to say what it was, but a specific engine supplier to a aircraft company had an engine have a blade out, and they called us up and said, "Hey, look, we need to go back and rerun our old versions of our ModelCenter workflows because we apparently missed something." And so they went back and were able to actually do forensics through ModelCenter to find, where were those problems and how do we fix them. So you're spot on with what you're saying. That happens.
It used to ruin people's sleep, worrying that when someone had a turbine stall. And I remember when Boeing had a couple aircraft, we didn't have any engines in Boeing, but they had a couple turbine stalls, and we were freaked out, totally freaked out, because you never know for sure. You do the best you can.
Right.
And you know what a horrific thing that is when it happens to an aircraft and a bird in flight.
Yeah, absolutely. And, yeah, I agree. I agree 100% with what you're saying. Any other comments or questions, or do we want to?
Well, when are you going to provide the direct facility? Since I asked the question, that's a feature you might want to have, which is you can go backwards in history and make sure as you have better models that you identify failure modes that could happen.
Right.
And there are two approaches. One is I don't want to know, which I think is unethical. And the other approach is, yes, we have to be proactive. And so some of your customers will probably want to be proactive. Yeah,
absolutely. And so if in that last video I was showing, when the analyst is going in and running his DOE, all the data that he's picking through is actually stored. So the responses from the runs are stored. And you can then go back and look through that archive and find that information.
Good.
Okay. All right. And of course, and what's nice about this type of tool is that, and we have some future technology stuff that we are working on, is that we will be able to actually maintain and organize all of the workflows that are created in a cloud environment. So I jokingly internally am calling it instant on with a workflow. So you can pick a workflow that was maybe done a year ago or 2 years ago or 10 years ago as it matures, and begin to turn it on and utilize that workflow from 5 years ago and see what results were done.
Now, where this is going to be super valuable is when we have a flight on its way to Mars and there's a failure.
Yep.
And what happens then is everybody runs around and scrambles to try to figure out what that failure they didn't anticipate was, know how to fix it. And now I think this is kind of a cool approach you have in that scenario, especially.
Well, you'd be surprised we get more calls than we like with people who find that where that kind of a situation happens. Like, we had a failure, may not have been life or death, but we had a failure and we want to fix it. And we have to go back and fire up a workflow. Can you help us? And so, because maybe the engineers have moved on to something else and the current engineers aren't the ones that built the workflow. They have to dissect it a little bit. So yeah, this call happens more often than not, but it happens.
Well, when's it going to be a feature?
I don't know. That's a Scott question, so it's good we have him on the call.
I do software, and over the years, I've seen the quality of software engineers go in the toilet because the average level of experience today is like a year, 2 years. And subject matter experts aren't in high esteem because there are not very many of them. So you don't want to compete with not very many when you're a lot of people competing. So even in the colleges, we teach really bad practices. So I can anticipate this in model-based systems engineering. Like I've been looking at the thing that Thales has, Capella. I can see that in the future, the quality of engineering is going to continue to go down. I don't think it's going to go up. And so
Yeah.
here's the problem we, as the gray-haired people, we have
Mhm.
to solve is how do we make sure that we don't have bad things happening 10 years from now because some professor taught some student they didn't have to do something, you know, like turning off interrupts.
Right.
And then bad things happen. So
Yep.
this might be a cool tool in the future to prevent that case.
Yeah, and I don't want to go too deep into this, but I actually have a colleague who has approached the Navy about looking into that for various ways to do training with the Navy, you know, in terms of different, you know, running through scenarios and things like that as part of a training exercise with this tool. So there's I love the way you're thinking about this because I think it possibly is the next stage that we can try to look at. So if you guys are okay, I'm going to go ahead and push through the next few slides, and we're going to get into systems engineering at this point and how that can be integrated to these analytical workflows to do validation of the workflow of the systems engineering solution. So I'm going to go ahead and push forward here. A few more slides left, and I think I will finish probably. I'll try to go a little bit quickly so that we finish about on time. Okay. So let's go ahead and start. So now we're going to switch gears and talk about the enablement of MBSE as tied to MDAO, a very hot topic in government acquisition and mission planning today. So you guys remember earlier I mentioned that mission planning is a capability that's moved forward pretty heavily. So I'm sure most people on the phone remember the dawn of mobile phones when phones were large and box-like. You could make calls and take calls reasonably well, and they did their job. Over time, the phones evolved. The new phones could not only make calls and take calls, but they also began to have new capabilities that you didn't even know you needed, but as of today, you probably can't live without. Things like emailing, texting, cameras, just to name a few. So the same can be said about today's systems engineering solutions. They do a great job of capturing behavior requirements and structure of your product design. But what if you could do more? What if you could connect your company's existing digital assets, those mission, physics, and cost models that your subject matter experts create, regardless of whether they reside in your organization or supply chain? What if you could connect those to your systems engineering solution? That is what ModelCenter MBSE provides, a way to enable MBSE so that you can perform high fidelity behavior simulation, requirements validation, and for very tough problems, optimizations that include trade studies at a system of systems level. So I know we can't necessarily do a show of hands here, but as a systems engineer, how many times have you struggled to find reasonable values to put into your system engineering models? As a subject matter expert, perhaps someone building an analytical mission or a cost model, how many times have you said, I'd love to have better access to the project requirements and the systems engineering model itself? So ModelCenter MBSE answers these questions by directly connecting system engineering solutions with the subject matter experts' digital models, essentially turning that digital shred into a digital thread, the true digital thread that's been promised. So one of the reasons why systems engineers do their systems engineering model is to determine if the requirements are satisfied. With ModelCenter MBSE, you can create satisfy relationships and share requirements with your expert digital models directly. So we provide within our tool set a way to actually connect those analytical values and variables directly to the systems model, and then you can actually set up satisfy relationships so that you can understand if you're hitting or satisfying a requirement. Once the analysis has been completed, you can see these values in your system, how they change in your systems engineering solution by down arrows, meaning values went down, but they can turn red, so meaning that they failed, or perhaps green, such as they've gone up and have passed. So our latest version of ModelCenter MBSE can also do conditional requirements for times when your requirement is not as simple as a pass or fail or greater than something or less than something. It can actually be conditional based. So let's say you discover an unsatisfied requirement. Utilizing ModelCenter's multidisciplinary analysis and optimization algorithms, you can perform sensitivity, design of experiments, optimization, risk reliability, and probabilistic analysis basically the algorithms that we showed earlier, you can do that against your systems analytics, your systems model tied directly to your analytical solution and find best solutions. So we've had customers today that are actually, they may have a change request that comes in through perhaps their PLM solution. The systems engineer will then look at it and dissect it across their systems engineering model, understand what changes and what solutions need to be run, hit the run button through ModelCenter's MBSE piece, and actually go off, run the solution. If it comes back with a failure, they basically can say, all right, what values around what are the minimum number of values that need to be changed to meet this requirement? And so they can run through these optimization algorithms and things that we showed earlier, and design of experiments, et cetera, to sit there and understand, how do we go about making the changes so that we can get rid of or basically work to this change request. Once that change request does pass the requirements, then it's passed now to manufacturing to go off and do their work. So this slide was presented by Mr. Guy Babineau in 2015, who at the time was the chief engineer at Northrop Grumman and one of the first organizations to adopt ModelCenter MBSE. He is now Northrop Grumman's Director of Engineering and Manufacturing Leadership. Per Mr. Babineau's words, Northrop Grumman was able to reduce costs, shorten the development schedule, and improve the quality of their designs. They also have been able to increase the satisfaction of their customers because the connection of analysis has allowed them to rapidly respond to customer requests. In many ways, they are winning more business now. Let's spend a minute looking at a fully integrated digital thread. So most organizations will start with requirements. These can come from doors or can be built already into your systems model. From there, ModelCenter MBSE acts as a bridge to the analytical models and manages the execution of the analytical models. As mentioned, you can then begin to play those what-if games with your systems engineering solutions with ModelCenter MDAO algorithms to the best combination of values that satisfy your requirements behaviors. Once you've met those requirements, you can then either upload them into your systems model or set as an instance to be uploaded after they've been checked by your systems engineer or others in your organization. Excuse me. So now we're going to walk through a recent ModelCenter model that was presented by Kentaro Sugiyama of Northrop Grumman. You saw his image earlier. Each box you see in this workflow is a subject matter expert simulation model or a nested workflow that they've created. That's all these boxes here. So in this case, you may start with a mission solution that defines your design space. This may also include a descriptive systems model. Then propulsion models from the supplier are attached. Keep in mind that these propulsion models may reside at the supplier within the ModelCenter. Within ModelCenter, they are black boxed, meaning that they run on the supplier's hardware with the supplier software being monitored by the expert at the supplier's location. And the only IP that's passed, really no IP is passed, I'm sorry, I didn't mean that. No IP is passed. The only thing that is passed between the two, between say a Northrop Grumman and a supplier would be the inputs and the outputs. So the inputs that go into the supplier's workflow that runs an analysis, and then the outputs that are brought back from Northrop Grumman. So this way, Northrop Grumman can benefit directly from the systems, from the supplier's expert models. So as you can imagine, a supplier is one who probably knows a lot about their specific product, like an engine, for example. You'd want those folks to make engine decisions, but you may need things like loads and thermal and electrical, everything else that you need to put into your aircraft. So it's a way of sharing these models without necessarily sharing all the IP. And if there is a question, of course, you can always pick up a phone or make a meeting and talk through things. Next, internal structure and design groups provide their models, as well as aeronautic designs and analysis teams and mass properties. In fact, it can also include cost models and things like that, so they can go and do cost versus performance metrics. So in this slide, you're actually seeing a Northrop Grumman analysis that's being run, the one we just described. We have things that we have integrations to CAD tools, which allow us to actually see or allow the engineers to see the updates that are being provided through the workflow on the CAD model. But the real value is down in the bottom left-hand corner, and the ability to make decisions against a large swath of data from the trade space that is created. You can do comparisons of inputs and outputs, for example, to maximize performance versus cost, weight versus fuel economy, etc. ModelCenter provides you with the ability to post-process the data and explore the best solutions for your product that meets or exceeds your customers' needs. And in many cases, now that it's tied to these systems engineering tools, they can not only say that we can meet the requirements digitally, at least, but ultimately they can say they can exceed it, so they can go through the process of upselling certain capability to the customer. So they may say, hey, look, we can carry this much weight, but guess what? If we make these modifications, we can travel this much further or this much faster. So we get this question often: what software can you integrate? And our answer is all of them. The logos you see before you are the most common solutions that our customers integrate. However, Phoenix Integration's philosophy is to provide the end users with the ease of use interface. With a little bit of training, you'll be able to integrate any simulation tool in your own bit bucket. In 2016, we did an audit with our customers and discovered that over 500 plus tools have been integrated. COTS, GOTS, in-house, every type that you can imagine. For this particular section of the presentation, let's focus on the systems engineering solutions. And by customer demand, the four most popular solutions you see before you have bidirectional integrations with ModelCenter. For systems integrations not shown, you can still integrate with them to extract information. For example, we have demonstrations on how we can do this easily with Sparks or Innosolate. So at this next section, we're going to run a small video to show you some how this works. Or I'm sorry, we're going to get to a video here, but before we demonstrate a Cameo integration, let me go through a few items. So basically, ModelCenter MBSE can connect to value properties, constraint blocks, and opaque behaviors. You can use all three or just one or the other. Pick and choose which method you prefer and which is best for your use case. Starting first with the direct value property integration, all you need to in your Cameo model are some blocks and value properties defined. No diagrams are needed. You can then connect those ModelCenter workflows to other automated models. And by using our easy to use user interface, on the left side, you'll find the blocks defined in your project and the respective value properties and parts. On the right-hand side, you'll find the variables defined in your ModelCenter analytical models. And then from there on, it's as simple as click, drag, and drop methods to establish these links, which are shown here. So essentially, you're just going to go and drag and drop particular values that you want to utilize in your systems model to your analytical or vice versa. Another integration method is through the parametric diagrams. This method is useful for when you want to connect multiple analysis to your systems model and would like to keep the connections explicit in order to manage the added complexity. To connect via parametric diagrams, we use constraint blocks, such as this one. Any or all of these constraint blocks could be linked to external analysis. And you can see here that you have various inputs and then outputs that are going to and from various analysis. To establish that connection, you can launch the specification as a constraint expression and then simply pick ModelCenter from the language dropdown. So ModelCenter is built, we have plugins directly within the systems engineering solution so that the systems engineer doesn't have to be necessarily a ModelCenter expert. And likewise, from the ModelCenter side, we have plugins or components that are built so that the analyst doesn't have to be a systems modeler expert. That brings up the same UI you've already seen in the previous slide. From here on, all you have to do is specify which analysis you'd like to connect and that parametric diagram to, and which can be locally or remotely, and then link the constraint parameters to the analysis variables. Moving forward, we can follow very similar steps to connect opaque behaviors and Cameo to ModelCenter analysis by simply selecting ModelCenter as the language for its specification, then using that same link editor UI. And if you're not familiar with opaque behaviors, they can be thought of as templates that can be assigned to any action within an activity diagram. What that means is you can more quickly create activity diagrams or simulate the behavior or system under different use cases or operating conditions, by using predefined opaque behaviors. Normally, Cameo supports certain opaque behavior languages, but you're quite limited in what you connect to. For the most part, it's only scripting tools and languages. With ModelCenter MBSE, you can connect your actions to any tool or scripting language, giving you a lot more flexibility in terms of the tools that you can use to simulate a behavior of a system, as well as the ability to connect actions to high fidelity tools such as finite element analysis or entire ModelCenter workflows with built-in logic that can kick off multiple analyses. Essentially, you can make the simulations more useful and more powerful and validate your systems engineering solution. Finally, ModelCenter MBSE also supports Teamwork Cloud projects in addition to local projects. If you're not familiar with Teamwork Cloud, it is No Magic's, the company behind Cameo, cloud solution that allows multiple systems engineers to access and work on the same model simultaneously. With ModelCenter MBSE, you can take that level of collaboration further by allowing multiple systems engineers to leverage and benefiting from your organization's analytical models. Your analysis tools can reside anywhere within your organization, and ModelCenter can do remote execution, which means that those analysis models can continue to reside with those subject matter experts. That is the teams behind them and creating them and maintaining them. So let's see an example. So now we're going to get into the demonstration. So let's take a look at an example of an existing systems model that was originally submitted by Robert Krause to the UD Mercy master's program. So this model covers a vehicle drivetrain, as you can see here. So I don't have an example directly correlated with the turbine, the wind turbine. So I'm going to step over to a vehicle, like an automotive in this case. So here's a view of the pre-existing systems model we borrowed. The CAD images are on the right. A block diagram, if you're familiar with systems engineering, is on the left that describes the decomposition of vehicle's driveline. We then create both high fidelity on the left and low fidelity models on the right for this driveline's half shafts and link them together to the systems model. The model describing the parametrics for calculating the sizing torque of the half shafts. We added a CAE model so that we can find the optimal geometry for the half shaft. So let me go ahead and start this example. So as mentioned earlier, we have our CAD models are described here. The systems model is described on the left. So one of the things we uncovered when talking with Bob Krause is that basically he didn't have time to utilize ModelCenter, and the tools that he was utilizing did not have the ability to connect to analytical models. But he provided us his work, his systems engineering model and CAD models, and said, "Have at it, see what you can do with it." So we went in to look at the half shaft piece. We built some systems engine. We built some CAD. We took the CAD, built some finite element analysis and some other components that we then utilized to connect to the systems engineering model. So in this case, you can see that we have the parametric diagrams we're connecting to from ModelCenter. And we're looking at the relationship between the engine torque, the weight of the vehicle, and the torque output of the shaft. And ultimately, we're going to set up a DOE, design of experiments. So we create an execution plan. And we run this. So what's happening in the background is when we run this from within inside of the ModelCenter MBSE solution, it's going off in the background and running those analytical tools and coming back with a response that either meets a requirement or doesn't meet a requirement, or in this case, you basically are getting values back to compare against what you expect it to have. We can set up a trade study, a DOE, just like we showed earlier in the ModelCenter Cloud instantiation of this. And we're going to bring across a few of the responses that we want to see, as well as the input values. We're going to set high and low values for those particular inputs. And then we're going to tell it the number of levels we want to run. In this case, we're going to run 9. I think it's a 9 factorial, I believe. So it goes off and runs an analysis, doing all the different various combinations of those inputs to see what the responses are. Again, each column is a run with a set of inputs at the top, responses at the bottom. Now we're going to go in and look at a contour plot, and we can see how the output torque grows with the engine torque. It is eventually truncated by the transmission. Torque is also limited by the wheel slip, and you can see the effect of the function of the vehicle weight. We could then follow similar steps for requirements verification, optimization of the system. At any point, if a good design is found, its values can be sent back to the systems model with the click of a button in the form of overwriting the default default baseline values, or saving as a new design instance, which is the more common practice. So as can be seen in this last video, we made an existing systems engineering model executable for validation. We used a systems model to drive the subject matter expert simulations, and we used the system model to perform a design of experiments to find new values of our design, which means instead of guessing at some of the values that the systems engineer might utilize in their model, you can take actual results from the engineering simulations and use them to populate the systems model, and also to then perturbate that systems model to find better solutions or perhaps different solutions and go in directions that you didn't expect. So to wrap up this presentation, you'll likely recall from the first generation cell phone and how it compared to today's cell phones. ModelCenter enables MBSE by connecting systems models to high fidelity engineering analysis so you can innovate your products. Most importantly, ModelCenter can culturally change the way the teams of discipline experts can innovate and find new solutions with a system of systems approach, utilizing all disciplines within your organization. And I guess that about wraps it up for this presentation. More questions, I suspect.
So folks, any question, you're welcome to unmute yourself and speak out.
You know, I really like your total presentation. This is Bill Lewis. It would be so much better if you'd have had this part first.
Yeah,
so
that's
so
good.
we could see the bottom line and then do the other stuff in that order. But I really like this last bit where you had an actual real model and you showed how it was tied into a different modeling system, not perhaps as capable. That's quite nice.
Yeah, we debate this every time we go into a presentation as to which section to show first. With AIAA, we expected to possibly be a lot more analysts and systems engineers. And so I wanted to focus on the analytical side of it as opposed to the system side of it first. But we can certainly switch it around in a future presentation as needed.
The best boss I ever had, he would get upset in Chicago and he would start pounding his giants, he's a huge man, on the table and he goes, "What's the bottom line?"
Yeah. Well, I mean, you know, the other piece of this presentation is conceptually, depending on who's in the room, there's a lot of pieces, a lot of moving parts, a lot of concepts that are brought out. So sometimes we struggle with what part to bring forward first. If we didn't bring forward the other components first, by the time we got to the systems thing, if we would have done this first, you might be going, "What did I just see?" So it's definitely it's a balance we have to play.
Yeah, but thanks for the presentation. I really enjoyed it.
Oh, it's our pleasure, and I appreciate everyone's fantastic questions, even the ones that kind of you know, stretch us a little bit on the way we think. So that's great. That's why we do these. Any other questions from the audience?
Just a comment, thank you very much for a great presentation and another glimpse into the future, because it's all about handling more complexity and abstracting it out into ways that humans can handle without, as I think Bill said, taking things for granted and ending up in trouble. So it's all there to be analyzed, but the tool allows you to manage it and explore more than we ever could in producing good products. So I think it's clearly the way of the future. I thought maybe you would make another reference to that Air Force aircraft. I was looking forward to some escape information, but
It's
I'll
it's
pass on that.
actually part of the eSave program that was done by Northrop, that aircraft.
Again, thank you. Great presentation.
Oh, you're welcome. If you guys go to our website under virtual events, I'm just showing you a real quick thing here. There was a presentation. There's a bunch of presentations that are coming up, and we do a very good job of Scott and his team do a very good job of asking customers to present. And this particular presentation was just done this past week by Parsons Technology Corp. And this really does show some state-of-the-art work with ModelCenter in terms of how we kind of hinted at this in terms of mission planning. So imagine the concept of being able to tailor aircraft or tailor the way an aircraft behaves with new capabilities based on the mission that you want to perform. And so in this case, they show how to use ModelCenter to look at what are the best conditions for satellites, aircraft, ships at sea, everything for asset planning for mission solutions. And it's pretty impressive. If you got to watch it, you'll be blown away by it. Scott, do you have anything else that you wanted to add before we end?
No, I'm good, Tony. I want to
Okay.
thank everyone for attending our presentation. And if you have any further questions, after the event ends, we'd be happy to answer those.
Yeah, absolutely. And hopefully you guys saw my contact info here. If you do have any questions, you're more than welcome to give me a call.